So this coordinate is zeta and this is xi. So if I want to be also like one by one coordinate, so what is the equation for this line in this coordinate xi zeta? Equation for that line, the vertical one.
Xi is equal to 0.
Xi equals to 0. And what is the equation for this thing?
Xi is equal to a constant, but what is that constant?
I said one by one. The simplest rectangle I want to make.
Okay,
I'm teaching this because there is a theorem that actually intuitively it's also true that you can always convert any region of n dimension into n dimensional cube. That's what I'm showing actually here. So this is, so what's the equation for this line?
Zeta is equal to 0.
This is zeta equals to 0, and this line
Zeta is equal to 1.
Zeta equals to 1. Okay, so now I want a map such that all these points over this line becomes this small segment that xi equals to 1. So to do that actually consider the boundaries. Here our for x coordinate is the boundary is like 0, 0 point, then a 0 point, then 0 b point. I want this point, I do not know what the coordinates are. Actually, I'm trying to figure those out. Maybe it's 0, 0. Maybe it's 0, 0. We can try for that as well. And the others are as I said. So this might be like my 0 was 1, 0, right? And this is 0, 1. And this might be 1, 1, like that. Okay. Now I want this point to be that point. So my A0 point maps to 1, 0, and my 0B point, 0B points maps to what?
A line. That means xi is
Maps
equal
to
to
line. Yes. So it's better to write in the opposite way. Instead of doing that, let's do this. So then we can actually tell that what's the equation for that line?
zeta is equal to 1.
Zeta equals to 1. So that's the set, and xi could be anything, right?
Yeah.
So xi 1, that's the point actually for that line. Xi 1, right? Xi is a variable.
But xi can't be anything. Can it be anything? Or 0 to 1?
Yes, it can be anything.
Okay. The whole line.
Okay. It's the whole line, yes. On all points on. So that's what I mean actually. It can vary from 0 to 1. So let's try some linear maps. Any big idea like what should be the map here? So why do this today actually? I'm not in my best shape. Okay, when zeta equals to 1, that every point maps to like 0b. So we can actually have so this is basically multiplying the whole thing by 1 minus zeta, right? When zeta equals to 1, that gives you 0 always. So my x value, x should be proportional to this.
Yeah.
Okay. Also, I need my y. X should be proportional to 1 minus this thing. So let's consider this one, and let's see how far it go, how far you can go. So also I want when it's 0 0. Actually, if someone's previous, like you, someone could help from previous class, because they had, like, we figured that out actually in that class. So how to map this thing consistently.
I have a question. Why do we need to parameterize in this way? I mean, like the previous one, why can't we just say
So
that
yes,
zeta?
we can do that, but then we have to like take care about the upper limit and lower limit the same way we did previously. That's okay also. That's also okay. We can do that. That's fine. But it's actually much more nicer to see that we can actually, if we can map this thing into this thing, we can use that xi zeta parameter and use that everywhere.
Okay.
Okay, and x value and xi value I want to be proportional. Like x value and xi value I want to be proportional. So I try this. X equals to 1 minus zeta times xi. If I do that, then when zeta is 0, oh, I'm missing a factor, which is a. Let's try. So when both are 0, that doesn't match. So if xi zeta both are 0, do they match? Yes, it does actually. Yes, when both are 0, xi and zeta both are 0, x equals to 0. That's for sure.
Yeah.
When when xi equals to something, but zeta equals to 1, xi equals to something, but zeta equals to 1, that gives us x equals to 0, which is true as well, right?
Yeah.
And I think that's it. And the rest. So let's try this. Y equals to zeta. B zeta. Does that work? So let's try for 4 points. So when it's 0 0, x is 0, y is 0, so it works. So these 2 points check, right?
Yeah.
What about this point? 1 0? If you substitute xi equals to 1, but zeta equals to 0,
It also
that gives you
A0.
a0. So that 2 point checks as well, right?
Yeah.
Now, if zeta equals to 1, that means this line, but xi could be anything that gives you. So it already covers these 2 points. So yes. So if you consider this line, then zeta is 1 that gives you x0, but zeta is 1 that gives you y equals to b. So that checks, right? So this point maps to. So we have figured out that this transformation actually works for this triangle to this rectangular surface, right?
Yeah.
So we want a more general thing here. It's a little bit generalization, not much, little bit generalization. So what can we do here? What kind of sorcery could help us?
Cylinder to plane.
Cylinder? No, we do not have a cylinder. We still have a triangle like this.
Oh, okay.
So we want this point to be somewhere, that point to be somewhere, that point to be somewhere, like that. So obviously we shrink one of those edge when we make it rectangle. So the better way to pick is, let's have a general 3-dimensional transformation that makes this this cube into a rectangle. Like it's a pyramid shaped, right? In 3 dimension, if you use general coordinate transformation, so make this thing into a cube, right?
Is it a cube? I mean, all is
No.
same. Rectangular. What is it called?
So this is your x-axis, this is your y-axis, this is your z-axis, right?
Yeah. Oh yeah,
This is
it will be cube because
so yes, it's a 3-dimensional thing. Let's make a cube out of it.
okay.
How about if we substitute z is equal to 0 in the plane equation, and what is left we can just call it a variable. I mean, I'm just talking about the projection of the plane in the xy plane.
Oh, so take a projection of that. You're saying
Okay.
take a projection of that and then map onto it. Yes. That's the way cleverer idea than I have. Yes. So how to take it? So what he's saying is, in 3 dimension, you have like this. So out of that, take a projection of that. So first we need a map between this plane to that projection plane. So what's that? Just setting z equals to 0 won't help. You need to make a projection from the top to the bottom point.
That's not point. I said that the plane that intersects with the xy plane, and it intersects through a line, right?
Yes, we're talking about actually plane, and we're trying to make that plane into a rectangle. We are
no. Just listen. That given plane intersect in the xy plane, right, in a line.
Yes.
And we can choose that line to be a new axis.
Yes, we can do that.
And then think about the other vertex to be the vertex 0, b, something like that.
That would we need a transformation for that, but that would be complicated, right?
Okay.
But I think the other one is easier actually. Take a projection of that thing on the plane, and we already know how to take that.
But we need a normal vector of the plane, and don't we?
No. It's just geometry. So do not introduce any vector or anything here. We are given with a surface equation. We are given with a surface equation, which is what's the equation of the surface?
Twice x plus 3y plus 6z
Twice x plus 3y plus
plus
6z equals to
what?
equals to 12. Okay. So when we are on that corner, that z equals to 0, and xy are also 0. So we want a connection between this point to the 0, 0, 0 point, a linear map between the two. So here in exterior calculus, like figuring out these maps are actually difficult.
For every point of that plane and the corresponding point of on that xy plane, they have same xy coordinate. Just
Yes.
the difference is on z. So we can get that point by as Arafat said, z is equal to 0 and same xy.
Yes. Yes. That's the projection. Yes. So we have a UV, and so out of this equation, actually, we need to figure out what are those, like that this equation here, that line represent that we want, like this 2 point actually we need, right? These 2 endpoint. What are those? What is this point?
Which point? What is your cursor? Okay, this point. This is,
That's the x-axis.
okay, x-axis. That means y and z is
1
0.
and 0 are 0, so that's 6,
X
right?
equal to 6, yeah.
So yes, this point is u equals to 6, but v equals to 0.
Yeah.
And then for this one, it's 3, right?
It's
1.
4.
So it would be 4. So
Yeah.
u equals to 0, but v equals to
4.
4. Okay, great. We have figured it out. So now here, instead of xy, we have like our uv. So we want a transformation u equals to something, v equals to something. And instead of AB, we have like 6 in one case, and for B, we have like V in another case, right?
Yeah.
Okay, that's the. So now you substitute everything over there. Actually, write down the equation of surface in terms of that. So Z equals to that. Actually, no. We all we need like the limit for u and v. That's all. So here is the equation of surface. Here is the equation of surface, and actually x and y are related by this relation. So x equals to this, y equals to this. We need something else actually. We need our z to be 0, right? For this.
Yeah.
We need our z to be 0. Or okay, let's just think about let's think about it again. So we have a map. We actually need a map from this plane to the projected plane. So the projected plane is represented by u equals to x, v equals to y, but z equals to 0. That's the important constraint. So all the z value need to be mapped onto z equals to 0. But no, that's not a transformation rule, right? So we
But
need
we can set
transformation.
w is equal to 0.
Hmm?
We can set another parameter w is equal to 0.
W equals to 0. No, that won't work. That won't work. That won't work. So the problem is like here we have like 3 parameter on 2 dimension. 3 parameter on 2 dimension, and that's constrained by these two relation. So we can figure out our z from here actually, right? What is the z value? What's z?
12 minus
12 minus
twice u of
actually,
x.
right? 2 minus half y minus 1/3 x, right?
Yeah.
So that is the equation for our plane. That is the equation for our plane, and with reparameterization, that becomes like z equals to like how z is determined in through like u and v. That is 2 minus half. Instead of y, I write v, that is 4 zeta, and instead of x, I write 6 into 1 minus zeta times I, like that. So that's our z. So that's the equation. So when you encounter z, you write that z in terms of the other two variables, and these two variables run from, so xi runs from 0 to 1 and zeta runs from 0 to 1 as well. That's how we have handled this thing. So now we are ready actually. So our surface is like confined at this thing, and the parameter, the surface of equation is this, and we just write everything in terms of like x, y, and z in terms of like xi and zeta. That's all. Okay. So now we have our parameterization, we have our field. So now we are ready to actually integrate that thing. So to integrate, we have to integrate beta, right? And what is beta that we have just figured out? What is beta? What is beta?
H is z d
Hmm.
y of x dz. dy wedge dz
dy wedge dz plus
minus 12
minus
minus
12
uh,
12
dz wedge dx
dz wedge dx minus
plus 3y
plus 3y
dx wedge dy.
dx wedge dy. Right. So now we have an UV parameter. We have an UV parameter. So basically what we need to do is integrate beta over the given region, which is integration 0 up to 1, integration 0 up to 1, piercing of beta with delta p by delta xi with delta p by delta zeta. So remember, it could give you a minus sign overall. That's because of the choice of our xi and zeta. So the way you have parameterized the surface. So if you parameterized it counterclockwise, it'll match with your vector calculus result, and if you parameterize the other way, you'll get a minus sign. So it's hard to see though which one is your xi and which one is your zeta, but I think it's still counterclock. So d xi d zeta. Okay, so now I'm not going to screw up this part, delta p over delta xi and delta p over delta zeta. I'm not going to use chain rule to change that. So I can do actually the other way. I can actually use chain rule to change dy dz and perform like change the beta as well. Which one do you want to do? Do you want to change your beta in terms of new coordinates? I think that will be the simplest one.
Okay.
So let's figure out dx. Let's figure out dx in terms of those variables. So if you take d over there, what do you get? Dx would be 6 1 minus zeta d xi, then then 6 xi minus 6 xi d zeta. Is that correct?
Yeah.
Okay, then dy is what? It's simplest one, right?
Or
Or
zeta.
or d zeta. And then dz, what's that?
And to see the expression minus 2 d zeta
Minus 2 d zeta. Then
2 minus 2 1 minus zeta d xi
minus 2 1 minus zeta d xi. Then
2 xi
plus 2
dz.
xi, right?
Yeah,
Plus 2 xi, yeah, plus 2 xi and d zeta. I hope everything's correct. So that's okay. Now we also need dy wedge dz, dz wedge dx, those parts.
Yeah.
Because I have to evaluate that thing. So dy wedge dx, what's that? Dy wedge dz, what's that? It has two parts of zeta, right? Zeta over here, zeta over there. So only thing you'll be left with is minus 4 times 2 is 8, right?
Yeah, plus 8.
Actually, I'm considering xi coordinate, so plus 8 1 minus zeta d xi with d zeta, right? That's just one thing, one single stuff. Okay, those who aren't able to see it, so we are actually taking wedge product between this thing and this thing. So it has two zeta terms. It has two zeta terms. Actually, we could simplify dz, right? So dz can be rewritten as minus 2, 1 minus 2 zeta d xi, then
plus 2 into xi minus 1 d zeta.
plus, or actually I should do this thing as well. This is plus 2 into zeta minus 1 and then plus 2 into xi minus 1, right?
Yeah.
Okay, that's how we can rewrite it. And the only part, like you take wedge product, dy wedge dz is this term. So this is 8. Did I make a mistake? No. I switched that thing as well. So let's write this way. That's better. Okay, let's evaluate. So dy wedge dz is minus, because I'm considering this times that, so minus 8 zeta minus 1 d xi wedge d zeta, right? I've switched the orientation, that's why I got the minus sign.
Yeah.
Then dz wedge dx equals to dz wedge dx. So how many possibilities would it have? Two possibilities.
Yeah. D zeta with d xi and d xi with d zeta.
Basically just one thing though. Okay, so and what's that?
It is
This
12 psi zeta minus 1.
12 1 minus zeta.
Yeah, 12 1 minus zeta.
Which way are we doing? Z.
D xi with d zeta.
Yeah, so 1 minus. Tell me if it is correct or wrong.
I have xi here. Don't you have a xi dx?
Let's write it explicitly. Yeah, because we are confusing many things. Okay, so yes, so this times this times that, right? This term times that term. That's what we need to do.
Okay.
So dz is the first one. So twice xi minus 1 times 6 into 1 minus zeta. 6 into 1 minus zeta. D zeta which d xi. This is one term. And another term would be this term with this term, right?
Yeah.
Minus 6 xi 2 into 1 zeta minus 1. So z is the first. So d xi wedge d zeta, right? Now
Yeah.
let's simplify it because it'll simplify a lot. So let's factor out this xi times zeta, d xi wedge d zeta. That's part. And then we have, so for this section we had like 6 minus 6, right? So minus 12 xi zeta plus 12 xi, right? Is that correct? Is that multiplication correct?
Yeah.
Minus 12 xi zeta plus 12 xi. Okay. Then this part, so it's already 12 times something, right?
It's
12 times
minus
xi.
12. It's just minus 12. And
Oh, we have a yes, it's minus 12 because we switched that thing as well. Yes, minus 12 times
uh,
I minus 1 into 1 minus zeta. So please perform the multiplication. Xi minus 1 times 1 minus zeta. What's that? It's xi minus 1 minus xi zeta plus zeta, right?
yeah.
So if I substitute that, then minus 12 xi plus 12, right?
Yeah.
Then
Plus
plus 12 xi zeta, and then
minus 12 zeta.
12 zeta. Okay, so these two terms cancel out. These two terms cancel out,
Yeah.
and we're left with just a small term, that is, if you factor out 12, that will give you 1 minus zeta, right?
Yeah.
And you can actually do the other way, zeta minus 1. So minus 12 zeta minus 1 d xi wedge d zeta. That you got. Okay, so the most complicated one is done, and the last one. So dx wedge dy, which is basically you'll have this term with this term, right? So it will be minus 6 1 minus 6 1 minus what? Zeta.
Yeah. Zeta.
Zeta, then d xi, which I have a 4 term over there. So 4 into d zeta, right?
Yeah.
So it becomes like, it is 1 minus or zeta minus 1. It should be zeta minus 1. I've taken a minus sign. So zeta minus 1, that's what I wanted to write. Okay. So actually it's the bad way I have written because every term has a minus sign. Okay. So it becomes like 24, right? So let's recollect. Recollecting our basis forms. So dx wedge dy, we got in a better way. Let's write in a better way. 24 1 minus zeta d xi wedge d zeta. That's one. Then dy wedge dz. What's that? It's 8 into 1 minus zeta dz d xi wedge d zeta. Then what?
12 1 minus zeta.
Dz, no, dz wedge dx is 12 1 minus d xi wedge d zeta. So see, all of those are the same basis, right? Those are the same two-form basis. So we can, when we are adding things, when we are calculating beta, we can actually factor out everything, right? So beta, it was a little bit complicated form. We're almost done actually. So just help me out here. What's that?
It was 18z.
18z. Then we like
dy
time
dy with dz.
dy wedge dz. So it will be like 8 into 1 minus zeta d xi
dz
wedge d
with
zeta.
dz.
Okay,
Then minus 12
minus 12
dz with dx.
dz wedge dx, which is 12 time 1 minus zeta d xi wedge d zeta. Let's take over here.
Yeah.
D zeta.
Then it's 3y.
3 xi.
3y.
3y. Okay. 3y.
Dx with dy.
Dx wedge dy. What is that? It
24.
is 24 times 1 minus zeta. I'm actually done here. D xi wedge d zeta, right?
Yeah.
So we can actually, you can see, we can factor out all those d xi wedge d zeta. So if you factor those out, d xi wedge d zeta, then you're left with what? This part, 18z. 18 times 8, what's that? 96.
18 times 8. It's 144, I think.
It's 144, okay. Yes, it should be a square thing, right?
Yeah.
16 times 9, yeah, 144. 144z, which I have to substitute later. 1 minus zeta, then minus
144.
144 plus 144 zeta, right?
Yeah.
Then here,
Then it 132.
24 times 3.
Oh, sorry. No, it's 72.
72, yes. 72y into 1 minus zeta.
Yeah.
Then we have d xi with d zeta. Now let's substitute y. Y, what's that? What's y?
Y is 4 zeta.
4 zeta. So 72 times 4 is?
It's
Just
420.
have a calculator. What is 72 times 4? Anyone? Help us out.
288.
218?
288. 288.
Yes, 288. Then we have zeta, right? Also, we need to substitute our z over there. And what's z? Z was a little bit complicated, right?
Can't we factor out 1 minus zeta?
What was z? I actually forgot.
Uh, 2 minus
Just tell me here, like I'll write it down, and then z equals to 2 minus
half y.
y by 2 minus x by 3, right?
Yeah.
I think that's correct, right?
Yeah.
Okay, so if you substitute that, then 144, then 2 minus, oh, actually you need to tell me z in terms of xi and zeta, not the other things.
2 minus 2 zeta.
2 minus 2 zeta,
And then what was the x? It was 1 minus zeta. And
we calculated it, man. We calculated it earlier. Where did you do that?
6
Uh,
into
Here.
6 into 1 minus zeta into xi.
So which is 2 into 1 minus zeta into xi, right?
Yeah.
2 into 1 minus zeta into xi. Minus 2 into 1 minus zeta into xi. Is that correct?
Yeah.
Okay, let's substitute. So then minus 2 plus 2 xi zeta. Then again 1 minus zeta. It's a long algebra, that's the problem. Minus 144 plus 144 zeta minus 288 zeta plus 288 zeta squared. Then we have d xi with d zeta, like that. Now if you multiply the first one, it becomes 288, right? Minus 288 zeta. Then actually there are two terms, they cancel out, right? I need not to worry about that two already.
actually, I don't think they do.
Oh, I made a mistake over there. That should be a xi. Okay.
That's correct.
Minus 288 xi plus 288 xi times zeta. Then again the same thing with a minus sign and xi squared, or xi power increased. So minus 288 xi plus 288 xi squared, then minus minus plus 288 xi zeta minus 288 xi zeta squared, right? I believe that's correct. Then plus minus 144 plus 144 plus 144 zeta minus 288 zeta plus 288 zeta squared d xi with d zeta. Now we are almost done. So which term cancel out? Are there any? Actually, they reinforce instead of cancelling, isn't it?
Yeah.
I don't think any term cancel out here at all. So at least we can factor out 144 out of every term, right? That's a every term is multiple of 144. So 144 times 2 minus 2 zeta. That's so stupid. Okay. So linear in like power 0 in everything. So here is 1, here is 2. So 3, right?
Yeah.
Then xi. So here is 1. Do you see any xi anywhere else? Just xi?
No.
So it's minus 2, right?
Minus 2 xi.
Minus 2 xi, yeah. Then zeta. So here is minus 2. Here is minus plus 1. So overall I have minus 1. Then here is minus 2. So I have minus 3, right? Do you see any other term? Oh,
Yeah, the second last.
this one. So
Minus
how?
5.
Minus 5 zeta. Okay, then
Xi zeta.
xi zeta, yeah. So
4.
this is 1, this is 1, so 4. I don't see any other, right? 4
No.
xi zeta. Okay, then zeta squared.
4.
Here is 1, here is 1, yes, plus 4 zeta squared minus, the only
2
term
xi.
is 2 xi zeta squared. Oh boy, it's long algebra. Okay, okay, we are done. We are done. So now this is our beta. This is our beta, and if we so the integral of beta was what? 0 up to 1, 0 up to 1, piercing of beta with delta p with delta xi, which delta p with delta zeta, d xi d zeta, right? That's the parameterization. So when you pierce that thing, see here I have like just pierce with delta p tilde by delta xi, which delta p tilde by delta zeta, which is when you pierce with beta is this part actually gives you just 1, right? So we are
Yeah.
left with the rest actually. So factor out 144, like take that 144 out of the integral. So you have to integrate this thing. 3 minus 2 xi minus 5 zeta plus 4 xi zeta plus 4 zeta squared minus 2 xi zeta squared d xi which d zeta. No, not wedge. It's just ordinary differential d xi d zeta. Now there are no like dependent limits, so you need not to worry about which integration you need to do first, which is you need to do then. You need not to worry, you just do it, integrate by partially, right? Perform a partial integration directly without any worrying about anything else. So if you do that, if you perform xi integration first, then as I can see 0 up to 1, then 3 xi minus xi square minus 5 xi zeta plus 2 xi square zeta plus plus 4 xi zeta square minus zeta xi square zeta square. d zeta. Do you agree with that? We're almost done actually. It's just a straightforward integration. Okay, so if you integrate, so we have in exterior calculus, we can always pick our upper limit and lower limit to be 0 and 1. So that's a real advantage. So you can actually integrate like after substitution, when you see xi is just 0, right? Also, if you do not see xi, that's also 0 because upper and lower limit cancel. So you get 144 with substituted upper limit, right? Only. So that is 3 times 1, which is 3, minus 1, minus 5 zeta, plus 2 zeta, plus 4 zeta squared, minus zeta squared. Just simplify it. By simplifying, you get 2 minus 3 zeta plus 3 zeta squared d zeta. If you integrate that, you get 144 times 2 zeta minus 3 by 2 zeta squared plus zeta cube, right? 0 up to 1. So you just worry about the upper limit, and that will give you 144 2 minus 3 by 2 plus 1. And what's that? 4 minus 3 plus 1, which is, oh, it's over 1. How come? Did I make a mistake?
Yeah, 4 minus 3 plus 2.
Oh, yes, 3 plus 2. Yes. So it becomes like 3 by 2, right? 3 by 2 times 144, which is half of 144 is 72. 3 times 72 is what?
216.
216? Yes,
Yeah.
this is the result. You see, it was so simple.
The result is actually 24.
We made a mistake somewhere, like in the factor.
But I have a question. Did we do just all these things to get that limit 0 to 1?
Yes. There are several things. That limit 0 to 1 also. You are here not dealing with multiple multiple coordinates. You are just dealing that much coordinate you need. Only 2 coordinate you are dealing with.
But we could do just with our projected area, which was just x and y. That the limit wasn't 0 to 1.
Yes, but then you have to like take the upper limit as well, like consider that upper limit. So yes, this might be a little bit. So what's the answer?
24.
So I think I missed some like factor somewhere. That's why this happened.
Maybe.
Yeah, at least this thing is proportional to 74, 24, right?
Yeah.
Okay, so long thing short is actually applying exterior calculus is not that simple in many cases, but when you do the theory with it, it's actually looks beautiful. That means I did not have much time to introduce. So next day we'll see divergence and curl. So what we'll see is for divergence, the exterior derivative is enough here. Exterior derivative would be enough. So like d would be like d of alpha would be like some curl of something, and d star alpha would be equivalent to like taking divergence. So in terms of exterior calculus, electromagnetism will have a geometric meaning, direct geometric meaning, like why Maxwell equation holds, it lies in the heart of that charge is conserved. So that's why we have a really nice form of Maxwell's equation. So that actually like embedded in Maxwell's equation, that conservation of charge. So it will be seen from here. It might be difficult for a while because a lot of things you have learned this same thing, but in a way different manner. But that's the trouble here. You have to like relearn everything.
Yeah.
Can you figure out where did I make a mistake that actually gave us the something multiple? I think here it was something.
Do you really want to do that?
Actually, like last time we did this kind of problem and without any much trouble. Yeah, there are trouble. Like I have to do this kind of calculation, obviously, but it wasn't this much off. I think what happened is I missed some like signs here and
Yeah, maybe.
that actually messed the whole thing up. Okay, whatever, you got the idea. You got the idea of how to do it.
Yeah.
Yeah, I made a mistake somewhere. The result is 24 only, right?
Yeah.
So there should be some terms cancelling, like particularly here. Okay, no problem. You'll encounter this kind of problem in your exams, so you'll learn eventually. Any questions so far? Today's class was a disaster, I agree, but did you learn anything at all? It was a disaster.
It was about definitions of exterior derivative and exterior integral and their applications.
Yes, it's the definition, like we set up the definition such a way that it matches with the original way of integrating things. So the thing we got here, you do not worry about Jacobian anymore. You just change the coordinate and Jacobian is handled by your exterior calculus automatically.
Yeah.
So that's one aspect. Another is you can always make your coordinate transformation such that in your new coordinate, the new variables only runs from 0 to 1. So you have to be clever about your mapping.
Yeah.
So question, can you map a sphere of radius c? So the equation is x squared plus y squared plus z squared equals to c squared. Like the bounded region, the three-dimensional volume bounded by this surface, can you map that into a rectangular area? Can you map that? It's a sphere.
We can use theta and phi.
You can use theta and phi. So it's a volume. I said the volume enclosed by this. So answer is yes. Yes, you can. So in that case, your R runs from like 0 to C, and your phi runs from 0 to twice pi, and your theta runs from 0 to pi. And if you want those to be 1, 1, 1, you could do that. Like you just divide the new variable, divide the variable by the upper limit. That will be the case. So yes, you can convert your volume or your area or any region into a rectangular one, which doesn't have any like combined upper limit, like combination of upper limits like that. A function like upper limit as a function of something else.
We don't need to divide with something, because we don't need 1. It's 0 to
Sorry?
C. Do we need to divide and make this limit?
You could do that. But 0 to 1 is actually more simpler. Like it's simpler than dealing with
0 to C.
0 to C. I wonder where did I make mistakes such that it was off by this amount. I think there is a plus minus that actually screwed the whole thing up.
Maybe.
Okay, figure it out and tell me where did I make a mistake next class. It's your homework for this session. I made a mistake somewhere, like some plus or minus actually got screwed up. The way here the transformation is correct, as I can see. Like we checked already, right?
Yeah, we checked it.
Okay. Anything else? Any questions so far? Okay, bye then. See you next week. Okay. I believe like that won't be this much disaster. So let's hope for the best. Okay, bye.
Bye. Thank you.